Okay, we're back with problem number 1, and we're going to continue on with our next part. What I really want to do is find out how much tension or compression is in each one of these members, and then once I find out how much force is going on inside of these, then I can decide what size of member I need there. So in order to do that, what we're going to do is we're just going to look at one corner at a time, and I'm going to start by looking at corner A. So what I'm saying is if I take my free body diagram originally and I just cut it off where all I can see is this little dot right here, what is this corner pin right here feeling? So I'm going to put a little dot here, and this is corner A, and I've marked it as at corner A so I know which corner I'm doing. Well, at corner A, I feel this AY, which was my reaction force. And if we look down here at our summary, we knew AY was 100 pounds going down, so I'm going to put that force on there. And then also what's happening at corner A is this member here, which I'm going to call AC, is pulling on that corner. We're going to make the assumption that all of our pins are in tension. So I'm going to draw it that if this one is pulling on the pin going this way, I'm going to draw it like this, and I'm going to make this assumption that it's tension. So this is AC. I'm going to make a little note here. Assume tension. And to assume tension, it needs to go away from the point. And then also at this corner here, I have this bar pulling up on the pin, and that one we're going to call AB. So I have AB going up. Nothing else matters. Notice I'm not doing this stuff up here. This is just like when we talked about free body diagrams before. You have to pretty much cover everything else up and say, what does A know? All it knows is that it's got this reaction here, this bar here, and this bar here. It doesn't know anything else going on in this problem. So this is our free body diagram that we're going to be using for this problem. Now we're going to do the sum of the forces in the X and the sum of the forces in the Y, just like we did earlier, but we're looking at this drawing right here. Well, what is the sum of the forces in the X? Well, it says AC, and it's going in the positive direction. And is there anything else there? So the sum of the forces has to be equal to 0, so AC has to have 0 force in it. In the Y direction, what do I have going in the Y direction? Well, I have AB going up, and I have AY, which is 100, going down. Down is negative. So here's a little baby algebra problem. I can solve that one. Add 100 to the other side, and I find that AB equals 100. So I found two of my forces there. I'm going to draw out my little example thing here, my final answer. I know that this member here has 0 force in it. And I know I just labeled that wrong. That's C, sorry. This is B. I know this one has 0 in it because I found it right there. And I know AB, this one here, has 100 pounds force in it. So I'm going to write it over here, my member forces. AC equals 0 pounds force. So this really is not tension or compression. This one here, AB, is 100 pounds. And because we got a positive 100 here, we know it is in fact in tension. So this one is in tension. Now in order to find the missing side here, I'm going to have to do another point, because this point A doesn't know anything about this side over here. So to find the last side of it, I would have to choose another point like at C. And now we're just considering what's happening here at C. Well, I have two reaction forces there. CX, I found earlier. Let me move it here so I can see. CX is going 200 to the left. And CY is going 200 pounds up. I also have here at C, this tension in AC, that was AC, but we found that AC was 0. So I'm going to draw it in here, but this one is 0. AC is 0. I found that right there. Then I also have this one going at this diagonal. And I'm going to kind of draw this a little dashed line here. Because can I do sum of forces in the X and Y with something going crazy at an angle? I can't. So I need to break this one into the part of this one that's going up, we'll call that BCY, and the part that's going to the side, we'll call that BCX. So I'm breaking this one into its two components. We did that before with vectors. So now I'm just going to do my sum of the forces like normal. My sum of the forces in the X are, well, I have CX, 200 that way, so that's negative direction. And BCX, that's in the negative direction. And that's it in this direction, because that one's 0. So I find BCX equals negative 200. Now I'm going to do the Y direction. I have CY going up, which is 200. I have BCY going up. And that's it in the Y direction, so that's equal to 0. So I find BCY is equal to negative 200. Well, remember when we did vectors? I really want to know what BC is, and I have BCX and BCY. Well, if I draw these, I'm going to draw them in the negative direction because these are both negative. Really, BCX and BCY are like this, and BC is going like that. Well, what kind of triangle do we make there? We make a little right triangle, so I can just use Pythagorean theorem to find what BC is. So that's 200 squared plus 200 squared equals BC. Toss it in your calculator, and we get that BC is equal to 282.8. And these were both negative, so this one means this one's negative. When I get a negative answer for one of these, what it means is it's not in tension. I assumed tension, but I got a negative answer, so that means it's really in compression. So we found that BC is 282.8 pounds of compression force in it. So when I picked a member for that side, I would need to pick a beam there that could withstand 282.8 pounds of compression. That's all there is to this. We just finished the whole truss problem.